Okay, so what we were doing on Friday was we were looking at the correlation coefficients of sets of data so that when we graphed them we could see how tight the data was, how straight of a line it made, and we did some problems where we approximated the correlation coefficient, and those were that was example 1, but you guys didn't write them in your notes, based on what the graphs look like, right? So if the points were going in a downward slope, that meant that it had to be negative, and the tighter they are as a line, the closer to 1 or -1 they get. Do you guys remember this? So in number A, because it was all pretty tight, we decided that the correlation coefficient had to be -0.9. In B, it was making a positive slope, but the data wasn't super close together, so we decided that it had to be 0.07. And then in C, the one that we looked at, they didn't make any kind of line at all, so there was no correlation. So then we started by giving you some data, and we started calculating the correlation coefficient by hand. So the data that you got is actually listed at the top of your handout, so we're going to use the points -3, -3, 1, 2, and 3, 4. So the first thing that we need to do is determine the mean of the x values and the mean of the y values. Now, we already did all of this work. X bar came out to 1/3, and y bar came out to 1. Okay, so I want you guys to write those in, even though we already did some of the work. So this was the mean of the x values and the mean of the y's. And then the next step was to determine the difference between each data value and the mean for both the x-coordinates and the y-coordinates. Okay, so that was our next step. Okay, so let's do the x's first. So the first one was, the first x value was -3, and then we subtracted 1/3. Now, -3 is the same as -3/1, so to get a common denominator, we multiplied top and bottom by 3, and that gave us -9/3 minus 1/3, which our first value gave us -10/3. We did the same thing for the next x-coordinate, which was 1, so that was going to be 1 minus 1/3. 1 is the same as 1/1. So multiply top and bottom by 3.
They have different tests.
So that's going to be 3/3 minus 1/3. So that was 3/3 minus 1/3, which came out to what, guys? 2/3. And then the last x value was 3. So that was 3/1 minus 1/3. If you multiplied top and bottom by 3, that was 9/3 minus 1/3, which gave us 8/3.
Where'd you get 1/3?
So the next thing we're going to do is the exact same thing, but for the y's. So we're going to take our first y, which is -3, and we're going to subtract the mean of the y's, which was what? 1. So -3 minus 1, so what's that give you? -4. Box it just so you don't lose it. Okay. So will you guys do the same thing now for the last two y's? So you're going to do the same thing for 2 and for 4. Okay, guys, so for the second y value is 2. So we're going to do the same thing, 2 minus 1, which gives us 1. And then for the third y value, what did you get? 4 minus 1, so you should have got 3, okay? The next step tells us, so I'm going to scooch it up just a little bit, tells us to determine the product of the differences in each pair, and then sum of those products, okay? So we're going to take the sum of the x differences times the y differences, and it's going to be the corresponding one. So we're going to multiply -10/3 times its y correspondent, which is -4. But we're going to add them all up together. So this is going to be -10/3 times -4 plus, what would the next one be? 2/3 times what? Times 1 So I'm just pairing up the first x and y, and then the second x and y, and then plus, what would the last one be? 8 over 3 times 3. Okay. So let's multiply all of these together. These are all, does everybody agree, negative 4 over 1, 1 over 1, and 3 over 1? Okay. So when we multiply them together, negative 10 over 3 times negative 4 over 3, what's that going to give me? Negative 10 over 3 times negative 4 over 1, sorry. 40 over 3. Plus, what would the next one be? 2 over 3. Plus, what would the next one be? 24 over 3. Okay, so let's add all of these together. 40 plus 2 gives me 42, plus 24 gives me 66, all over 3. And does that reduce at all? Yeah, what's it reduced to? 22. Okay. Box that too, just so you don't lose it. Okay, so that was as far as we got on Friday. So we just did everything with the numerator. Now let's work on the denominator. So here's the denominator piece. Remember, it looks scary, but it's really not that bad. So the first part is to determine the sum of the squares of the differences. Okay? So let's look at the x's first. So we're doing that xi minus x bar, and then we're squaring it. But did we already do the work for this part? Yeah, that's all of these values. The negative 10 over 3, the 2 over 3, and the 8 over 3. So to do the x's, we're going to take those differences and just square them. Okay, so the first one is going to be negative 10 over 3 squared. Now when we're squaring them, that means we square the top and the bottom. So negative 10 squared would give me what? 100. And 3 squared would give me 9. Okay. And then let's do the next one, which would be 2 over 3 squared. So that's going to be what? 4 over 9. And then the last one would be 8 over 3 squared, which comes out to 64 over 9. Okay. Will you guys do that for the y values for me? Okay, so for the y's, what did you guys get for negative 4 squared? Good, 16. What about 1 squared? 1. And 3 squared? 9. Okay, so we found the squares of each of the differences, and then the last part says they want us to determine the sum of those. So we have to add all of these up, okay? So I'm going to do it just off to the side of each one. So 100 over 9 plus 4 over 9 plus 64 over 9. 168 over 9? Okay, so Jonathan said it comes out to 168 over 9. Does that reduce at all, guys?
Yes.
I'm thinking, you want to try 3? How many times does 3 go into 16? 5, with a remainder of 1, and then that would be 18, so it would be 56 over 3. Box that. Okay, so we're doing the sum. What would the sum of the y's be? 16 plus 1 plus 9. 26. Box that. Okay, so it all comes out to each sum. Okay, so then we're almost done. Last part is to determine the square root of each of those sums. So we're going to take the square root of 56 over 3, and we're going to take the square root of 26. So let's write that in. Square root of 56 over 3 and the square root of 26. You are going to need to use a calculator. On this one, I'll do it for you guys. So you would do 56 divided by 3, and then take the square root, and it should come out to 4.32. And then the square root of 26 would come out to approximately 5.099. And the reason we went to one other decimal is because if we were to round to here, everything would all round up. Okay, so let's leave it at 0.099. Okay. The very last part is to determine the product of those two values. So we're going to take the square root and multiply them. So that's going to be 4.32 times 5.099. Which is going to come out to 22.02768. I know, it's a lot. Box that. We will, but we did, so what we did so far, I'm going to zoom out so you guys can see it all. We looked at the numerator, and the whole answer that we got in the numerator all came out to 22. So the entire numerator came out to 22, okay? The entire denominator came out to what? 22.02768. So what we're going to do, very last step, is what's written at the very, very bottom. Put the numerator and denominator together and simplify. So it's going to be 22 over 22.02768. So don't round it until the very, very, very end, which is approximately 0.099. I'm sorry, 0.9987. So that's your R. So does this data make a pretty straight line? Yes, because it's a big decimal, right? It's close to 1. So that's going to be our R. Let's put R as approximately. Okay. Okay, so the last couple of examples, you would use your calculator to get the values and plug it in, which you already have the steps taped in your notes. But because we don't have the class set of graphing calculators, I'm going to give you the values, and then we're going to plug them in together. So I give you this big set of data with the different years and the percent of obese children in those years. So in 1971, 6.4% of children were obese. And in 1976, 5.0% of children were obese. In 1988, so they didn't study this for another few years, 10.5% of children were obese, and then 1999, 14.8, 2001, 16.7, 2003, 17.4, 2005, 17.8, 2007, 18.1. So what's happening as the years go on? It's getting increasing. Any thoughts as to why? McDonald's in particular? Yeah, stuff like that. So let's first determine what our different x's would be. So we always start our first one with x equals 0. So if 1971 is our x equals 0, what would 1976 be? X equals 5, 5 years later. What about 1988? 32? We would do 88 minus 71, right? 1971. Here, let me zoom in some more. Yeah. We're going to do so 88 minus 71 would be 17. What about 1999? That would be 28, right? Yeah. Okay, and then then we start counting by 2 years. So 2001 would be 30. 2003 would be 32, 2005 would be 34, and 2007 would be 36. Okay? So remember, you have to make sure that your first one is always x equals 0, and then you count from there. So if we were to plug all of this stuff into the calculator, you would get an A value of 0.38, a B value of 4.7, and then it would say R equals 0.9851. So what would our linear regression equation be? Y equals, remember it's AX plus B, so it would be 0.38X plus 4.7. Okay? So here's our R. Here's our Y. So the question is this linear regression an appropriate measure line for the data set? Tom says yes. I agree with him. Does anybody have know the reason? The correlation coefficient is almost 1. So is this a pretty straight line if we were to plot all of our data? Yeah. So is this equation pretty accurate? Yes. So because the correlation coefficient, let's just say R, is because the R value is so close to 1, there is a strong correlation . Okay, so something like that. So the closer that your R value is to +1 or -1, the stronger your correlation, so the more appropriate that line of best fit is. So I'm giving you another chart that tells you the amount of an antibiotic that remains in your body over a period of time varies from one drug to the next. So I'm giving you some kind of antibiotic, and I'm telling you how much of the antibiotic is in your system at a certain time. So when I give it to you, you get 60, this one is milligrams, of that antibiotic. So they give you a shot, and there's 60 milligrams of that antibiotic in your system when they give it to you. After 6 hours, there's only 36 milligrams left. After 12 hours, there's 22 milligrams left. So what's happening? It's decreasing, which makes sense, right? Because your body starts using it. So after 18 hours, there's 13 milligrams left. After 24 hours, there's 7.8 milligrams left. At 30 hours, there's 4.7, 36 is 2.8, 42 is 1.7, and 48 is 1. Now, because our time started at 0, will we have to change any of these X values? No, because they're already given to us. So what we're going to do is I'm going to give you A, B, and R. In your groups, I'm going to have you write the linear regression equation, so Y equals AX plus B, and I want you to tell me if it's a good line of best fit or not, okay? So if we were to plug all of that into the calculator, like we did last week, you would get an A of -1.1, a B of 42.3, and an R of -0.8832. Okay? So guys, what was the linear regression equation? Y equals? -1.1 x plus 42.3. Good. So that's your equation. Who determined that yes, this line of best fit is good? Who determined that no, it was not good? Okay, let's talk about it. -0.8. Is that close to 1, or to -1? Somewhat, but is it super, super close? No. So do you think this would be a super great line of best fit? No. So I would say that no, because the R value is not close enough to 1 or to negative 1. Okay, and if we were to graph this, I'm going to show you what the graph looks like. So if we were to graph it, the data looks like this. What kind of function does that look like, guys? Exponential. So would a linear line of best fit really be the best line of best fit for this data? No, why not? Because it looks like an exponential, right? So because this looks like an exponential function, a linear line of best fit would not necessarily be the best thing for this data. Okay? So that's why the R value is close to 1, but it's not close enough to make it that it's a line. So really, you want your R value to be like 0.9 something. Okay?